All right, welcome back. So today we'll be still looking into AC circuits. This is continuing on what we learned last time. We talked about each element, the resistors, inductors, and capacitors, how they behave in AC circuits. Now we're going to put them together and then see how they behave in the AC circuits. And then we also talk about resonance and also the power factor of AC circuits when we have these elements in them. So let's dive in here. So last time we say for a resistor, it just acts like a resistor the same way as it does in DC circuit when it's placed in AC circuit. Now, if you have inductor or capacitor, they also react to the voltage you apply similarly, but we call them reactance, so XL and C. So all these three combined, we call them impedance. Collectively, when they are all presented in the circuits, AC circuit. So for example, you have those three: resistor, inductor, and capacitor. They all are in the AC circuit here. So the collective reactance to this voltage you apply is called the impedance. So then the current in the AC circuit now also behave similarly, just to Ohm's law, where your current I of sub zero, this is similar to I of max. Okay, so the maximum value should be the voltage maximum divided by the impedance of the whole circuit. And then if you are looking at the RMS current, should be just RMS voltage divided by the Z. Okay, so this is again just Ohm's law, similar to Ohm's law. All right, so we have those three at the same time in the circuits. Let's take a look then. So when we have the three resistor or resistor, inductor, and capacitor, they are all the same in the circuit. We know that for the current and the voltage, so for a resistor, they are always in phase. Okay, so that means when current peaks on the resistor, voltage also peaks. Now, if we have an inductor, inductor's voltage actually peaks before the current. So then here, the sinusoidal function of the voltage on inductor then looks a little bit different from the resistor. So it's leading the current of the circuit. The capacitor, the current actually leads the voltage. So the voltage will peak later comparing to the peak time of the current. So it's then this guy. So the combination of these three, the voltage on the three, so we add them up. So then it will be something in between. So not necessarily peak at the same time as the current, but it could be lagging the current, or in some cases be leading, depends on how much ahead of the capacitor's voltage compared to the one on the resistor, or how much the voltage on the inductor is lacking compared to the inductor. So it's basically a combination of those three. So this guy, the voltage is on the inductor is actually ahead of this guy by 90, but the voltage on the capacitor is actually lagging the voltage on the resistor by 90. So then these two are always having opposite signs. So you'll see that when your voltage on the inductor is positive, the voltage on the capacitor then will be negative. Okay, so the overall voltage then on the circuit will follow this relationship. Okay, so these two are always opposite to each other. But then this guy here, so this is the formula. So this is basically kind of the Pythagorean theorem, if we could call that. So then the voltage, overall voltage peak should be the peak value of this guy, and then plus the difference of these two. Okay, depending on which one is bigger, which one is smaller. So the voltage on the inductor and capacitor, they are either 90 degrees ahead or 90 degrees behind. Okay, so then the peak value on the resistor is not always the same as the difference of these two. Okay, so they are always differ by 90. So that means these two actually form like 90 degree like that. Okay, so then the total, the overall should be the one side square plus the other side square, and then add them together. So this is kind of so if you draw this out, so V this is absolute value of V of on the inductor minus V on the capacitor. Okay, and then on this guy here, this is the voltage on the resistor. Okay, so these two add up. Okay, because they are 90 degree each to each other. So this is kind of like a vector. You add them up because they are not in the same direction. So they will add up to be this guy over here. Okay, in the just this diagonal direction here. So this is like A square plus B square, and then that gives you C square. Okay, so because of that, because the factor that the maximum value of the voltage on the resistor is either 90 degrees before leading the difference of these two, or 90 degree ahead of these two. Okay. All right. So because of that, now also according to this Ohm's law, or kind of um, the similar expression to Ohm's law here. So maximum voltage total is equal to the current total times Z, and this guy V total or maximum on the resistor is actually IZ, or I0 times R, the maximum I times R. Okay, and then you square it, so you get I0 square R square. And then also on this one, this will be I0 times XL, its reactance. And then this guy will be I0 times XC. So it will be this one. Okay. So you can see that. So that's I0, I0, I0 across. So you can actually, and then they are all square. So you can pull the I0s out of the square root. So it becomes I0 square root of R square plus XL minus XC square. Okay. And this I0 and this I0 would actually cancel. Okay, so if we cancel that I0 and this I0 out, we'll end up with this expression of the total impedance on the RLC circuit should be R squared plus XL minus XC n squared. Okay, and then this is again similar to just the Pythagorean theorem. So where you have R like that, and then the difference, absolute value of XL minus XC. Okay, so depending on actually kind of depending on various factors, the inductance, the capacitance, and then the frequency of the circuit. Okay, and then we'll give you which one is bigger, which one is smaller, but they should form a 90-degree angle to between the difference of these two and the R. Okay, so that's why you got that expression there. All right, let's take a look on the example here. Okay, so this one says find the RMS voltage across each element in an RLC circuit with R equal to 8.8 kilo. Okay, so there's a lot of prefix here. Make sure we convert them appropriately to the SI units. So kilo ohms, and then capacitance 0.12 micro farad, and then L equal to micro. Okay, so those two are, this is L, this is the C, this is R, and it says the RMS, okay, RMS voltage given is 115 from the generator, which has a frequency of that. Okay, so this is the frequency, this is the VRMS, okay, and LCRC. All right, so we are looking for the voltage, RMS voltage across. We know the total, this is the total, okay? We are looking for each of them. So first, I think what we need to do is maybe we can kind of sketch this circuit. Okay, so for an AC signal, this is what you do. You do a circle, and then with this tilde line, that means it's alternating, or kind of looks like kind of sine or cosine function. And then we have this R, okay, and zigzag line, and then this is like the L and then the C will be just two parallel lines. Okay, so this is our R, our L, and our C. All right, so to find the RV RMS on each of them, we can actually find the current, the RMS current for the total. Okay, so the strategy is to find IRMS because V RMS for each of them for the R is IRMS times R. Okay, and then we are given R, so we can do that. And then V RMS on the L should be again I RMS times XL, and then for the capacitor it will be times XC. Okay, V RMSL equal to I RMS times XC. All right, so we are given R and we are given C and L, so we can actually find XL and XC. Okay, so XL, let's find XL first. XL is equal to 2 pi F times L. Okay, so we can just plug in numbers, 2 pi times 60 Hertz times 28 milli, so 10 to the minus 3 Henry. That will give us just about 10.56 ohms, okay, on XL. And on XC, XC is a little bit different. It's 1 over 2 pi FC, okay? So we do 1 over 2 pi 60, and then times 0.12 by micro 10 to the minus 6, okay, on that. So then we have, in this case, this would be 22,105 ohms, okay? So we need to look for IRMS, right? IRMS is the total IRMS that will be actually equal to the VRMS, and we are given that divided by Z. Okay, so for a RLC circuit, so we need to find the Z. So Z, we can find it. Z will be equal to square root of R squared plus XL minus XC and square. Okay, so we now have all of those three. You can plug in the numbers here. 8.8 kilo, so 10 to the third, that to be squared plus XL is 10.56 minus 22,105 and squared. Okay, so this gives us 23,782 in ohms. Okay, so that's the total Z. Now we can calculate our IRMS. That will be 115 volts divided by the Z, the 23,782 ohms. All right, so that would be 4.836 10 to the minus 3 amps. All right, now we have that. We can calculate the this ones here. So we can calculate this, okay, because we now have our IRMS. Okay, so then V RMS on the R is IRMS, which is this guy, 4.836 10 to the minus 3 amps times 8.8 kilo ohms, again 10 to the third. Okay, so that gives us 42.6 volts. Okay, so that's on the R, and on the L should be the IRMS we got again, minus 3 amps, and then times the XL, which is 10.56 ohms. Okay, so this gives us just 0.0511 volts. Okay, And the next one, the V RMS the C on the capacitor, 4.836 10 to the minus 3 amps, 23,782 ohms. Okay, that gives us 107 volts. Okay, so we have all of those solved. Now, if we look at these three voltage we get, okay, so this one, and this one, and compared to the total of 115, okay, so apparently those three do not add up to be 115, okay, and that's what we want because if you remember earlier we said those values, they do not peak at the same time, okay, that means they do not also have the average values at the same time. Okay, so in that case, if we look at the VRMF's total, this should be similar to VRM's peak. That should be equal to square root of VRMS on the R square plus VRMS on the L minus VRMS on the C and score. Okay, and then let's just quickly check if that's the case. Okay, so 42.6 score plus 0.0511 minus 107 and score. And then when you punch these numbers into your calculator, indeed it gives you 115. Okay, so that's just double check at the end. Okay, so you might want to do that every time at the end to just make sure if you don't get that number that you are supposed to get, then maybe one of the calculations or some calculations that you did was not right. Okay. All right, so that's this example. Let's go back to the PowerPoint slide. And let's just move on to the next topic here on the resonance of RLC circuits, okay? So we said that for if you have a RLC circuit, so the total impedance from the circuit is this guy here. So you can see R squared plus XL minus XC. And your current, either is your RMS or your volt or your peak, then it's the V. Okay, so for the average RMS, it's this guy, VRMS divided by square root. Okay, R squared plus XL minus XC square. Since your XL is a function of frequency, so XL is 2 pi F times L, and your XC, okay, so this is XL, this is XC, okay? So it's also a function of F. Now, what happens if these two equals to each other? Okay, so if these two equals to each other, then your denominator will be minimum, okay? Because then it's just R in the denominator. And then anything else, if this is not equal to 0, even it's negative, if you square it become positive, so then the denominator become larger, okay? So there's a condition when these two, your XL equal to your XC, so then this equal to that, then you have minimum denominator or minimum impedance, which will give you maximum IRMS, okay? And when that happens, the frequency is called the resonant frequency. Okay, so you set up these two equal to each other. So then you kind of solve for your F naught. Okay, so multiply both sides by F naught. So that means this F naught get moved to this side, and then divide both sides by 2 pi and L. Okay, so then you'll get F 0 square on the left hand side equals to 1 over 2 pi b squared times L times C, okay? And then solve for F0, you take square root. So then this 2 pi squared, the square will be canceled, but the square root will be on L times C. So then this is your resonance frequency, okay? So when that happens. All right. So that means when that happens, you have maximum signal, okay? All right. Now if so when that happens, your resonance frequency F naught, then your IMS is minimum. So it depends on what resistance you have in the circuit. You have smaller resistance, then you'll have bigger current. If you have larger resistance, you will have smaller current. Okay. Um, let's take a look on how the application of this through this example here. Okay, so basically your radios, if you have an old-fashioned radio, like a tunable one in the car, not a digital one. Okay, um, so it's it has an RLC circuit in it. Okay, and the frequency that gives you different frequencies. If your frequencies match up with the radio signals, then you get resonance of the signal to the circuit. Okay, so then the signal will be enhanced. Now other frequencies will be suppressed. Okay, so that's how the radio works. Okay, so this one says for your AM radio, a resonance at frequency range of between 500 and 1650 kilohertz. This is compared with a fixed. So you have a fixed inductor and then connect to a variable capacitor. Okay, what range of the capacitor is needed? Okay, so you turn your resonance frequency, which is the F naught. Okay, that can be tuned. Let's see, maybe here. All right. So it has a range of 500 kilohertz to 1650 kilohertz. And basically, F naught is equal to 1 over 2 pi square root of LC. Okay, so we are given that your L is fixed. Now, what's the range of your C? So basically, we can replace F naught here with this expression. So basically, this is going to be just 500 kilo. Let's just put 10 to the third there, and then we'll just forget about the units for right now. That's equal to 1 over 2 pi square root of LC, and then that's equal to 1650 times 10 to the third. Okay. So then we are looking for C, the range of C. So what we want to do is we wanted to square everything, okay? Because everything is positive. So when you square them, the signs of equal symbols will not change. Okay, so that's that. And then in here, now this will become, if you square, this will become 4 pi square times L times C in the denominator. Okay. And then now you can multiply everything by 4 pi square times L to isolate C. Okay, so similarly there, I'm not going to copy those numbers down, but you can calculate if you want and then put them down here. Okay, so multiply everything by 4 pi square L. Okay, and then multiply by 4 pi square L to get rid of 4 pi square and L there. So what we have now should be just on this side is 4 pi square times L, which is 1 times 10 to the negative 6, okay, Henry, and then times 500 times 10 to the third square. That's equal to 1 over C, and then that's equal to, again, 4 pi square times 10 to the minus 6 times 1650 times 10 to the third and squared. Okay. All right. So now we have this guy here. We want to find C, so we will do inverse of everything, inverse of everything here, and then inverse of everything there. However, when you do inverse, the unequal sign actually do change, okay? So then you'll get that the two signs will be flipped, all right? Now you can plug everything into your calculator at the end. Your left-hand side should be equal to 0.101 and times 10 to the minus 6 farad. I'm doing 10 to the minus 6 because this can be then expressed in as microfarad, greater or equal to the C and greater or equal to 9.3 times 10 to the minus 9 farad, which is nano, okay, nanofarad there, or you can say, so that's the range, or we can say 0.101 microfarad greater or equal to C, greater or equal to 9.3 nanofarad all day. Okay, so either way. All right, so that's on that. Let's go back to the PowerPoint. All right, so next, let's talk about the power consumed in the RLC circuit. So previously, if you remember, we said when inductor and capacitors, when they are placed in the AC circuit, they actually do not consume power, okay? So then all the power is consumed just by the inductor. So then power consumed here should be just the IRMS square times R, okay, the average power consumed. And this can be broken down into the IRMS square can be written as IRMS times IRMS times R. And one of IRMS will be V IRMS divided by Z. So then power will be V IRMS RMS IRMS. Okay, the root mean square quantities are V times R times R over Z. Okay. And here it's being called a funny name called cosine. Okay, so cosine of phi, cosine of phi is equal to actually R divided by Z. Okay. And then that's called the power factor. And then it has to do with a little bit geometry here. So if we have R, and then so let's say R here in this direction, and this would be absolute value of your XL minus XC if you recall earlier, and this would be the Z. I don't know why you always give me this wiggling line, but I'm actually trying to draw a straight line over here. Okay, so that's that, and then if you put it down here, this angle is the phi angle. So then it's actually referring to this. Okay, so the ratio R over Z actually it's based on this triangle here, okay? But that's called the power factor. So that's the amount, what's the amount of power consumed in the circuit, okay? Percentage wise, okay? So this is to the normally what you would have consumed, okay? So V IRMS times IRMS, okay, to give you back. Because you have L and C, so you are not consuming all the power. Some power is stored in the form of either magnetic field or electric field, okay? So then only partial of the power is consumed by the circuit. So this is called the power factor, okay? So power factor then is simply just your R divided by Z, okay? So you can calculate your Z and then do R divided by Z will be your power factor. All right, so let's take a look on the problem here. So this one says, determine the power factor for an RC circuit with R equal to 4.0 kilo ohms and then C equal to 0.35 microfarad that is connected to a AC generator with a RMS voltage of 24 and a frequency of 150. Okay, so calculating power factor here, we need to do so power factor is cosine. It's called cosine phi. cosine phi will be just R over Z. Okay. Now Z is equal to square root of R squared plus XL minus XC squared. Okay. Now this is only a RC circuit, so that means there's no RL. So you can put 0 as your RL there. Okay, so that's just 0. And then this will be R squared 4.0 times 10 to the third. Okay, so prefix will be important. Always remember that. Squared plus, now it will be just only XC. Okay, XC is 1 over 2 pi F, okay, 150 hertz. And let's see if I can write it better. Times 150. And then times 0.35 10 to the minus 6. Okay, so all these are under the denominator. And we want to square that and square root of the whole thing. Okay, so this gives you your z as actually just 5.0 10 to the third, and that should be in ohms. Okay, so then power factor should be equal to R, which is 4 times 10 to the third ohms over 5 times 10 to the third. Okay, that will be equal to 0.8. Okay, or 80% for that. All right. Okay, so now back to the slide here. All right, now if you don't have R in the circuit, if you just have L and C, so that means the circuit is not consuming any power. Okay, so then the energy will be stored in the circuit either as a electric field or magnetic field, but it's going to be if you have now initially the capacitor charge, then the charge is going to flow through here, creating current. Okay, and then you'll have a magnetic field pick up here, and then once all the charge is discharged here, you will have maximum current on this guy. And then the current will keep flowing. Then this side will become positive, charged. This side will be negative charge. So then you're building up electric magnetic energy in the electric field form, and then so on and so forth. And so going back and forth, back and forth. Okay, so then that will be just oscillating of energy, like converting energy from electric field to magnetic field. Okay, and this is similar to mass to attach to a spring. So then kinetic energy converted to potential energy converted to kinetic energy, back and forth, back and forth. So kind of oscillation that way. Okay. All right. So what we learned today, we take a look at the RLC circuit in the AC circuits, RLC combination in AC circuit. So maximum current will be maximum voltage divided by the impedance. And RMS current will be equal to RMS voltage divided by the impedance. The impedance is R squared plus reactance from the inductor minus the reactance from the capacitor, and then square it, okay? And then square root the whole thing. When we have frequency at the resonant frequency where the XL and XC cancels out, so your current will be enhanced, okay? So that's when you tune to a radio signal, that's what happens. Okay, so that signal is enhanced, other signals will be suppressed. We look at power factor. So power factor will be basically cosine of phi, which is defined as R divided by Z, because power is only consumed by the resistor, not the inductor or capacitors. Okay. All right, we'll stop there today, and then we'll come back another time. Okay, see you guys.